So we were talking about operational amplifiers. So in 301, we went through quite a bit about it, and we explained the purpose of operational amplifier, right? So there were two inputs, plus and minus, and we get outputs and we have a feedback. And we are now looking inside this op-amp. How do we design this op-amp using BJTs and CMOS? And what was the purpose of operational amplifiers? Why do we use this differential signal structure? We want to amplify the differential signals. So if I make this VID over 2, differential signal divided by 2, and if I make this minus differential signal over 2, so the input will be plus minus minus, so VID. So we amplify the VID, right? So this will be a function of VID. So A1 VID will be the output. But if we have a common mode signal at the input, VCM, well, the input is 0, right? Plus minus minus, VCM minus VCM is 0. So we won't be seeing any effect of the common mode. So in Elon Musk's company, Neuralink, so they embed chips inside to the brain, to the motor cortex. And there are these basically microelectrode chips. And from neuron to neuron, the signal is basically an action potential. You can think it like a digital signal. The signal gets amplified and we get the amplification of the input. But of course, there is certain noises and we want that noise to be common. If we just amplify one signal, we'll be seeing a lot of noise like this one. There will be a lot of noise and we will need to extract these action potentials. But if we have two signals and use an op-amp, now one signal will be this and one signal will be also having a similar common mode but have a minus differential signal, right? So minus differential signal means, so if we have a one signal like that at the input, this one, this input should be starting with negative polarity, right? It should start from here and here. So this point, common point, is VCM. It's like a DC. This is also DC. This is plus, and when it is plus, this one is minus, and plus minus minus plus. So basically we get to amplify this AC signal, but we don't get to amplify the common mode signal because they cancel each other. So this way we are able to cancel this background noise. So I explained to you these differential and common mode signals. The V1 and V2 can be written with respect to a common mode signal and a differential signal, okay? A common mode signal and minus differential signal. So as you can see in this slide, if we apply a common mode to this node and to this node, this is only a DC signal. This tail current is the main current that assigns the current to these branches. So if they are both same voltages at these gates, the currents through here and here will be ISS over 2, right? Because they won't be fighting each other. They are same voltages. And this voltage, basically X or Y, will be VDD minus this resistor times ISS divided by 2. Right? So as you can see, Vx and Vy, they will be same voltage. So if we apply same voltage, output differential will be what? This voltage will be what?
0.
It will be 0, right? Vx equals Vy. So Vx minus Vy equals 0. As you can see, even if we change VCM, the current on these transistors won't be changing. The only thing will be changing, if VCM increases, this node will increase voltage-wise. But the current is still same. And if this voltage increases, will this voltage change? So if I change the VCM, if I change this voltage, will Vx change? You know, as I mentioned, we have a king here. It's this tail current. He's the king. He says, whatever I drove currents, the current will be half of it here and here. And if I change VCM, looking in this formula, will my Vx voltage change? It won't, right? Because my VDD is same, my resistor is same, my current is same. So basically, this circuit tells you, hey, regardless you change VCM, as much as this is a strong current source means it has a big resistor, right? As you remember from cascode current mirrors, that's why we were using another transistor to make this R out bigger, remember? So as long as we use a strong current source with high R outs, this VCM change won't really affect your circuit because it won't change the current on this branch. It will only change this voltage, because your VGS minus VT depends on the current. So basically from the equation, saturation current equation, K times V overdrive, right? Assuming lambda is 0. In the CMOS, we have this equilibrium voltage. If we write that current formula, okay, this is ISS over 2 here. So ISS over 2 going through that transistor is, let's call this K times VGS minus VT, right? So there's a K over 2 here, sorry. So if we rewrite this, that's the equation. We call this equilibrium because VGS minus VT, when we apply common mode to both parts, this is the formula. This is how we find VGS minus VT, overdrive voltage. And equilibrium means neither of these branches are strong. They're in equilibrium, right? Same current is going through it. So we'll be using this formula a few times in the next slides. So going to the next slides, well, now we have a different thing to learn. There should be a minimum common mode output voltage. What does it mean? So minimum common mode output voltage means there should be a minimum voltage here that this transistor should be in saturation, right? We want it to be saturation to make the amplification. Well, we need to figure out what is the VDS voltage. VDS in saturation, what is the formula? Well, VGS minus VT should be what? So this is the saturation, right? So now looking in this formula, let's find the drain, VD. Well, VDD minus RD times ISS2 gives you your Vx, right? And this Vx minus V, let's call this point VA, is your VDS, right? So it's telling you basically, so this is VCM, VG, this S was VA, and minus VT. So, and this is VGS, right? So writing this, we know that VDS is bigger than VGS minus VT. And this writing this shows you the VCM should be basically can't be bigger than certain voltage. VDD minus RD ISS2 is basically setting a voltage for VCM. So for instance, there is a question here. A MOS differential pair like this has an input common mode level of 1.6 volts. So it's saying that VCM is 1.6. The current is 0.5 milliamps. VT is 0.5 volts. VDD is 1.8 volts. What is the maximum allowed load resistance? Well, just applying this, we rewrite RD. You can see that we can find RD. Why there is a maximum allowed load resistance? Well, if this resistance becomes so big, that means this voltage will drop a lot, right? Because there is a voltage. If this is like, this resistance is huge, this VDS will be 0. Well, we don't want VDS to be 0, right? Because then this won't be in saturation anymore. So this VDS voltage should be like as big as possible to have this transistor in saturation. Next slide. So one of these will be stronger. If Vin is bigger than Vin2, then as you can see, this part will draw more current. So as you can see in the x-axis, Vin minus Vin2. That's your VID, right? That difference bigger than 0. Well, as you can see, it will start to draw more current than ISS over 2. And if this goes like way high, like there is this limit I'll show you, then eventually it will start to draw all of the current. And same with the other branch. If this goes high, then if this becomes strong, Vin2 becomes more than Vin1, which means VID is negative, then eventually it will start to attract all the current. And this one shows the output voltage. When these inputs are same, we are at this point, right? Vin1 minus Vin2 is 0. And output will be here, which is VDD minus this resistance times ISS over 2. Let's say when this branch gets stronger, which means going this side, and then as you can see, there will be more currents going through here. And because there will be more current going through here, this Vx will get smaller, right? Because there will be more voltage drop here. So, but Vy will be bigger. Why it will be bigger? Because there will be less currents here. So this Y voltage will be bigger. So this is the characteristic. So when I tell you draw the characteristics of the circuits, what you draw is input is this, your VID, and output is your V out. So looking in this, you can see that your V out, actually your difference plus minus, for instance, let's look at here, right? This is VDD minus RD ISS minus VDD becomes minus RDD ISS, right? VDD is cancelled. And if you look at here, at this point, then Vx minus Vy, it will be RD ISS. So as you can see, at this part and at this part, we have the voltage settled at RDD ISS. So you probably will see something like, at VID 0, output is 0. But when VID goes plus, your output goes negative. When VID goes minus, output goes positive. Right? I will introduce you a new concept called virtual ground. Assume that we are here at VCM and somehow suddenly we apply this small signal voltage, delta V. It's very small extra voltage. And we apply the negative of that to the second port, right? And when we do that, because this ISS is strong, the fixed current, but when this voltage increase, what will happen is it will kind of follow, this voltage will kind of follow this voltage. So, and then this voltage decreased and it will kind of try to follow this voltage, try to follow this voltage. So you can think it like this. We are at this point and we are at the common mode. Let's say this is 5 volt. And this P point, let's assume, well, it's not there, but let's assume we are here because these voltages will be same when they are same. And when this voltage increase, basically, let me draw this way, this one, will try to go up. So it will go, let's say this is 1 volt increase. So this will also try to increase 1 volt. So we drop this 1 volt, and this from 7, it was 5. So this will want to be 4. So now we are 6, 4. Previously, this was 5. We would expect P voltage to be 5 volts, right? Now, what do we expect for the P voltage in this case? 5 volts, right? So this is called virtual ground. Basically, any change in the differential signal, plus and minus, doesn't really change the voltage of P, called virtual ground. So we can think that in AC domain, actually, because this voltage is not really changing its DC value. So even we are changing the AC at the input, this voltage is fixed. So in AC domain, how can I show this? DC is not changing. DC ground, right? DC is not changing. So we can just ground this when I go in AC. Remember, we draw circuits in AC domain and DC domain. When I draw the AC domain, there is this thing called half circuits. What you do is just cross the circuit like this from the half, like with a knife, and anywhere touching this pink line is ground. Okay, so here is ground. There was a part here, let's say there are resistances here. This would be ground, AC ground. Okay, you would ground it. Well, so if we compare a differential circuit with a common source circuit, you will see that we actually have 2 times of the current, because this is, let's say, VID over 2, and there will be ISS over 2 here. So the overall gain of the circuit will be basically GM-RD. We also have the same gain, GM-RD, right? If we just draw one circuit like simple this one. Well, then why are we having 2 times of the current, right? Most differential pair, basically, it dissipates twice the amount of the current of a common source stage. We have delta Vx minus delta Vi, when we have a small change of delta V here and a small change of minus delta V, the changes here in terms of voltage, delta Vx minus delta Vi will be minus 2gm RD delta V. And when we divide it to the change, V1 minus V2, which is 2 delta V, 2 delta V is cancelled. So as you can see, gain is minus GMRD. Basically, that's where it's coming from. This is same with the common source stage, but we are actually having 2 times of the current. A question regarding a CMOS amplifier. Saying that a CMOS differential amplifier has a voltage gain of 5, a power budget of 2 milliwatt, and it requires an input common mode level of at least 1.6 volts. This is the mu and COX. The lambda is 0. Basically, that means R0 is 0. R0 is infinity. And it says that VDD 1.8. So how can I start solving this question? So it's saying that VDD 1.8, and it's saying that a power budget of 2 milliwatts. So what is the power? Power is V times I. Right? Basically, a power budget means how much power I am having from this VDD port. Power is 2 milliwatts. V is 1.8. That means we can find how much current goes from here and here, which means this one, right? So this ISS, basically we found it. It's 1.11 milliamp. And because we found ISS now, we can easily find that the output common mode level, which is, because the output common mode is VDD minus RD times ISS over 2, right? And it's saying that the differential pair requires, the stage following the differential pair requires a common mode level of at least 1.6. So what's saying that the other amplifier we connect here requires a 1.6 volts common mode here, which means the output of this first amplifier, DC wise, it should be at 1.6. So if this is 1.6, we know VDD, we know ISS over 2, so we can find RD. So we did find RD, and then we need to find GM. And it's easy because we know the gain is GMRD. It says voltage gain is 5. We found the RD, so the only thing left is GM. So we found the GM, it's 5 over 360. And 5 over 360, we put it here. We know ISS, right? We know mu times COX. The only thing left would be width over length. And now we design it. We design a circuit, a differential pair that runs other amplifiers with 1.6 volts common mode voltage. Okay, this is the common mode voltage because there are transistors here, right? So we need to bias them. So 1.6 volts satisfied. Power budget 2 milliwatts satisfied by finding ISS, maximum ISS. And the gain 5 is satisfied by finding the GM because RD was limited by the 1.6 volt, right? So we found the GM, the transconductance, basically how powerful this M1 and M2 should be. So GM shows how strong it is. So basically we found GM, the others already given, like we found it, or yeah, it's given and we found it. So basically we designed the circuit to meet all these specifications. And actually this is what I do when I design chips. You are given these specifications. We said it's a power budget of 2 milliwatt. That means your circuits cannot consume more than 2 milliwatt. VDD'si sabit. Chip'in VDD'si, yani en azından bu circuit'ın VDD'si 1.8. O zaman şuradaki ISS'in olabileceği maksimum değer o power budget'ınız tarafından belirleniyor. VDD çarpı ISS küçüktür 2 milliwatt. Milliwatt'ı geçmeyecek bu devrenin consumption'ı. Niye? Bu 100 milliwatt olursa iPhone'unuz bir saat sonra ölür. Değil mi? Sonuçta these are circuits that consume power. Battery, this is like your battery, right? So this gets the power from there. So we need to design it as small current as possible. But with these small currents, we need to get good performance. ISS small means GM is small. Well, if GM is small, that means your amplification will be small, right? So we need to boost it with either width or with small length, which means improving technology. In your PSpice, I gave you 0.18 micro, right? Today's technology is 0.02 micro right now. So it's been scaled like in the last 10 years, of course. And there's UNCOX. UN is the electron mobility, which is kind of fixed for silicon. If you use a different semiconductor, you can boost it, like gallium arsenide in military. They use gallium arsenide, right? There are different ways to boost GM, but of course, all of them has some limits. Question? Aynen. This is for 2 milliwatt. Yeah, 2 milliwatt is setting your limit for ISS. So, next question. What is the maximum allowable input CM level if VTH is 0.4? CM'inizin maksimum alabileceği değer ne olur? VTH 0.4. Şunu anlattık. So VCM is this volt. VCM minus VT. VT buraya gitsin. VCM minus VT is, since they share the same source node with VDD. İki tarafa da S yazmayacağım. Şuraya minus VS yazıyorum. Onlar götürüyor. Dolayısıyla VGS eksi VT, emin anlattığım gibi VDS'den küçük olmak zorunda. Dolayısıyla bu equation'a koyduğumuz zaman zaten VCM için maximum limit çıkıyor. Okay? So if VCM becomes, for instance, bigger than 2 volts, then this circuit will not be in saturation anymore. Yeah, well, we were comparing these two circuits, right? So this is a good maybe exam question. So there is this differential amplifier and there is this common source amplifier. So, and when we look at the AC, we were cutting this and everything is ground. So this is ground, right? So we can simply look at this circuit in the AC domain. This is called half circuits, which I will explain in the next slides. But just to analyze this circuit, we can look at this circuit in the AC domain. And of course, in the DC domain, we also need to find GM. Right? If two circuits are designed for the same voltage gain and same supply, discuss the choice of transistor dimensions for a given power budget. So for a given power budget, that means same voltage, same supply voltage, they should have the same current. So if I call this ISS, or let's call it ISS, yeah. And this circuit is also ISS, right? DC wise. So now they have the same power budget. So given power budget. So VDD times ISS, VDD times ISS. The ISS over 2 is flowing here, right? From one circuit. So basically, this is half of this transistor's current. And looking at the GM, where is the GM formula? The ISS directly affects the GM. So, and the square root ISS, right? Then there's also width over length. So going to the, again, next slide, like same slides. So now we would say that, hey, well, I have ISS here, I have ISS over 2 here, but I want the same voltage. So then how shall I design these transistors, right? Well, of course, logically, you have to increase the size of this because you want to have the same voltage gain. And this is a good, basically, homework for you. For like maybe you can spend 5-10 minutes. This circuit has a gain of, let's call GMRD, right? Voltage gain. You know that already. And this circuit, so let's call V out over V in. And this circuit, because ISS over 2, well, we want this also to be GMRD. To reach to the same GM, the differential pair transistors be twice as wide as the common source stage, right? Because in the GM, when we look at the formula, it was 2K, well, mu COX. There's a width over length. There's a mu CX here. Let's call it K lambda. And the current through it. So if this is ISS and this is ISS over 2, that means the width should be 2 times for this transistor because we want the square root to be same for both transistors, right? So we have to compensate the less current by increasing the width of the transistor. And when we increase the width, we are able to get the same GM. What is the drawback of increasing the width? So if this width over length, for instance, for this one, it is 5 or 10. And now we have to design this for 20 microns. So a transistor, if you make it bigger, you bring something that you don't want. Like there are all these metals here, and then these all have interactions, right? What kind of parasitic interactions do they have? Parasitic caps. So the more the transistor gets bigger, the more the parasitic caps for the transistor. So what happens when those caps increase? The impedance of the cap is 1 over j omega c. Right? So if this cap increase, what happens to the impedance? Yeah, it goes smaller, right? 1 over j omega c is the impedance of the cap. If the c goes high, exactly this omega basically needs to be smaller, this cutoff frequency. So for this amplifier, you want to get a gain like this. But if you increase the width, now you cannot get a gain of like that. You get a gain of like this, okay? So this frequency, because the C increases, this frequency now goes lower, this cutoff frequency, where gain starts to drop. Well, why? I mean, the logic is simple, right? We have a small input here, and we want an amplification here. But this AC signal, if you have a cap here, a huge cap, let's say infinite cap. Burada sinyal görebilir miyiz? Yes, no. Buradaki cap çok büyük değil mi? Infinite dedik. Ne oldu impedansa? 1 over j omega c ise short oldu değil mi? Şimdi biz bunu shortlamış olduk. Burada nasıl sinyal göreceğiz? So when this VDS cap increases, well, what happens? This basically amplitude we want, well, it drops a lot, right? Because this cap pulls this voltage to the ground. Akım, hani şöyle düşünürsek, akım şuradaki output'tan gitmek isteyecek yerine şuradaki cap'e gitmek isteyecek. Well, so there is this strange curve. We explained it in the previous slides, and the curve was when the input is going one side strong, it was pulling all the currents, and if this one is strong, then this one was pulling all the currents, right? So, and if we take the IDD minus ID2, which is this currents minus this currents, versus V in minus V2, and if we drive the equations, we get to basically formulate this curve. Outputs in terms of inputs. It becomes a complicated function. And for those of you who want to learn where this function is coming from, it's coming from a bunch of equations. But the two important equations is V in minus VGS1, which is this voltage, equals to V in 2 minus VGS2, right? So it's this voltage, same. So one of them is this equation, and then the other important equation is, like, well, we already know that this current plus this current is ISS, right? So these two equations, then writing the formula for the saturation currents, we get to find this, and then we can write V in minus V in 2, V in 1 minus V in 2 in terms of the currents. Then writing this, there are a bunch of other equations, and eventually we get to have this equation. Okay, so looking at this equation, if V in 1 equals V in 2, right, if they are equal to each other, you can see that the currents will be same, right? ID1 equals ID2. So, and the other one is, you can tell me, hey, if V in 1 minus V in 2 is this, then this also goes to 0, right? At certain voltage here, I should see like a kind of current dropping like this. Important part here, what I want to mention, how much voltage I should increase compared to here so that I pull all the currents, right? So these are competing with each other. This one, V in 1, should be bigger than V in 2, this much, so that pulls all the currents, right? And that one is given to you as square root 2 times VGS minus VT equilibrium. We find this equilibrium voltage, right? And they are at the same voltage level with the ISS going through here. This is the VGS minus VT. VGS minus VT equilibrium is this. So if we multiply it with square root 2, then that's the voltage basically here. The slope shows your gain. But now, as you can see, your slope is getting smaller. Your current amplification is getting smaller because now you are out of the range. So if you are out of the range, even here or here, now your circuit is kind of saturating, right? You don't really get to see the benefits of your circuit, okay? And we don't want this. In power amplifiers, before the antenna, this is the most important problem, because in power amplifiers, we are dealing with really big signals. The input here is huge. We have to really boost the signal. And we need to really design very linear circuits, a slope that's fixed. But that's not the case. So we get to see some nonlinearity here. Always talking about CMOS. Well, the exact same logic works for bipolar, right? So because the logic is same, what the two transistors fighting for each other, and they have a common mode signal, so they don't fight. But when they have an AC plus minus, that fight basically, translates to current change. So one of the transistors, even if it is small, it attracts more current, but it's AC level more. DC level, it's same. So always think it like AC and DC, right? So one of them is having more currents and the other one is having less current. So DC level is always same currents. But when this goes little high, which means this goes little low because we apply differential signal as here, this current gets little stronger than this current. As you can see, it goes higher, it goes lower. And this is actually what is bringing the gain, right? At this point, we actually have a good amplification because it's linear. But as you can see, this is the voltage difference, the current difference versus voltage difference. And we have a good amplification here where it's linear. If you go back to the virtual ground concept is actually, this is ground because the actual delta V increase is not changing this voltage. Current increase is circulating here between these two nodes. So the example I gave you, this is 5 volts, this is 5 volts, this is fixed. If this becomes 6 volts, and if this becomes 4 volts, well, this is still 5 volts, right? Doesn't change, but you see the current flow from here to here, right? 6 to 4, from high voltage to low voltage. Yeah, it's exactly the same logic. This voltage may be going high, maybe this voltage going low, or vice versa, and it's creating a flow here. There is no extra current flow here. This current is fixed. So for bipolar, the only difference is actually in the CMOS, these voltages are found, right? We found those voltages. It was square root times something. That's
VGS minus VT equilibrium. And for bipolar, this actually goes to infinity. Like there is always some little currents flowing from the other transistors. Even this BJT here is stronger compared to other BJT. There will be always some current flowing in this one. Okay, this never goes to zero or like to that edge. So this is a good question. It's in the Razavi, you can check it. It's saying that we know the characteristics V out minus V out 2, V out 1 minus V out 2, and x-axis is V in 1 minus V in 2. So the characteristics was this one, right? Starting like this. So what happens when we double the tail currents? Instead of ISS, what happens if this is 2 ISS? V in max, ISS formülüydü. V in 1 eksi V in 2 max, V in max. Dolayısıyla ISS'i arttırırsak 2 katına ne olacak? Şurası square root 2 artacak, right? So we actually increase the range of the allowed input voltage swing. Now this limit increased square root 2 times more, right? And what happens to output? Well, V out 1 minus V out 2, the range is ISS times RD before, right? Because when this is no current here, this is VDD, and this is VDD minus RD times IS. So the difference between these two nodes will be minus RD ISS, right? Or RD ISS, depending on which one goes higher, RD ISS minus RD ISS. If we increase ISS to 2 ISS, well, it will go to 2 times of it, right? So the new curve for these characteristics. So I explained the virtual grounds, just quickly, briefly summarizing. This pinpoint is not really changing. This is virtual grounds in AC. So actually whatever AC current is happening plus minus delta I circulating between X and Y. Okay. And knowing this virtual currents concept, now I will again explain you the half circuits theorem. So half circuit means cut it into 2, do this. This becomes grounds, and you can just solve this circuit rather than solving the entire topology. And as you can see, we just write it. Input is VID over 2. This is the transistor. This is the ground. This is the RD. So GM times VID over 2 is the AC current. It gets multiplied with RD. So this becomes minus since it goes this way. So I put minus here, then multiply with RD. It gives the voltage, right? So then I divide this voltage to the VID over 2. These cancels. We get the gain GMRD, right? Well, of course, it also includes the R0. If we have a early channel length modulation, we'll have a R0 here. So drawing the small signal, of course, this GM currents, the AC current here, will flow both to this and to this, right? So these will be in parallel. So RD, R0, okay? So maybe I can draw it here nicely. But let's assume this one becomes minus, and this current flows, since this is ground, R0. So this current flows to both RD and R0 parallel, as you can see. And the VIDs over 2's cancel to find the gain. So it becomes, because R0 is big, we say this is the gain. So as you can see, we found the gain of this circuit, which is also the gain of this circuit. Okay, so you can look at it, how we draw the small signal. So for VID over 2, as you can see, it draws a small signal. So it also does the same thing for minus VID over 2 if you want, but we don't need to because we are doing the half circuits, right? So looking at only one side will be enough. How does it work in the common? Well, we have a current mirror here, right? It's coming from somewhere else. So that this is actually a transistor. Because it's a transistor, it's actually have a finite resistance, RSS. So when we do the RSS and when we we draw the common mode as well, just like we draw the half circuits, we gotta draw the common mode. So looking at the common mode, this RSS, we can connect these 2 points because they are common modes. They have the same voltage. And we write the RSS as 2 RSS and 2 RSS because their parallel becomes RSS, right? 2 RSS, 2 RSS. So this is 2 RSS, this is 2 RSS. So doing that stuff, you will be able to draw this half circuit. 2 RSS, 2 RSS become RSS. So instead of writing like this, we are able to write 2 RSS and we can draw this circuit, right? And drawing the small signal model, we have VCM because this is the common mode. So VGS at the source, we have 2 RSS and rest is the same. Like we basically drawing the small signal, AC domain. We again find the gain, right? And VO1 divided by VCM, as you can see here, is this one, GMRD divided by 1 plus GM2 RSS. So because RSS is big, doing some simplifications, canceling GMs and stuff, we get this, and we can write again minus RD divided by 2 RSS. Okay, and this is called common mode gain. So you apply a VCM and you look at the Vout1, and Vout1 divided by VCM is called common mode gain. If we have a current source here, this RSS is huge, so that your output in the case of the common mode signal applied is 0. But if it is not ideal current source, which is never ideal current source, it's always a transistor, so we always have a common mode gain. Okay, and we want this differential gain to be as much as possible, and we want this common mode gain to be as low as possible, because we want to amplify the differential signals, we want to not amplify the common mode signals. So there are some examples here. For instance, this one, it's a circuit that has these load inputs are applied to Vin and Vin2, and these are transistor loads, right? Active loads. And active loads means actually when you connect gate to the drain, this becomes like a resistor, like 1 over GM. So when we look at this transistor from here, what you see is 1 over GM, RO3, because you see this one, you see 1 over GM, and then there is this node, RO1. So simply, without writing the small signal, I can write the impedances at that node, right? This node, RO3, this node, RO1, and then, as I mentioned, this diode connected load, last lecture I explained a few times, as the impedance 1 over GM3. So, and this is the load there, and simply drawing the small signal of this half circuit in AC domain, right? I cut this. That means this is ground. So I just look at this circuit as here. And as I explain it, the circuit has a gain of, input times GM1 gives this current, minus of that gives this current. So this current flows all the resistances at this node. And all the resistances, equivalent resistance is this. If you don't understand how, you can again draw the small signal. Basically, we have an input. Input goes to the M1. This is the VGS. This is source. So it creates this current, GM1, V in 1. V in 1 is VGS, right? So that's why this is VG, this is VS. So this becomes GM1, V in 1. And this current is exactly this current AC-wise flowing just right here. If we take the minus of this, it will be minus GMV on, minus GMV in. And if we multiply it with the entire resistances, this one, and this one, that's the equivalent resistance. And when we divide it to V in 1, V in 1s cancel, and we get the gain. Mesela, this is example 2. So what we do is we cut it into 2, like a melon. So this is ground. So since this touches here too, it's ground. Okay. So we draw it. So this is the AC half circuit, or differential AC. Okay. So you also need to find the common mode half circuits, right? Basically, you gotta solve the circuits in DC domain. If I ask you, hey, calculate the common mode gain, then there is this thing called common mode AC half circuits, right? Which I explained it previously. And in the common mode AC half circuits, we don't really do this because we are not applying a plus and minus anymore. We are applying same level. And because it's same level, what happens is, just like here, actually you don't really put ground anymore, but you duplicate the common values which create that current flow. So 2 RSS, 2 RSS. Okay. So, and let's say we have a resistor here like that, right? Then, you cut it and this becomes open. Why does it become open? 5, 5. They want to be the same, right? So this becomes open, 5, 5. So if there is a resistor here, when we do the common mode, we just cut it. Like, let's put a common mode here. We cut it, right? So this becomes open. So this kind of becomes open too, but there is this resistance here, which we want to carry it to these 2 points. So we want to kind of like make the circuit equivalent to it. Okay, but this one, we cannot really do it. So then in this case, we have a resistor with the open node, which doesn't really make any difference because there is not really any current connected there, right? Any ground or any node connected there. Bunu biraz daha detaylı anlatacağım. Hani biraz anlamanız common modu ve hani differential mode, half circuit'ları zaman alabilir tabii ki. Another example. So if we do the differential, that's what we're doing examples right now. Well, this means this is plus, this is minus. So what were we doing? We were cutting this in the middle, and all these middle nodes are ground. And that means we divide this resistor into 2, right? We divide this resistor into 2. And as you can see, that's how we connect. The current sources open because they are DC. So RSS over 2, ground, RDD over 2, ground, right? So now this becomes your half circuit. You can simply solve the gain of this circuit, and that will give you the gain of the entire differential amplifier. The signal is common mode signal, and we look at the output due to this common mode. Common mode signal, we want it to be small, right? Because we don't want to amplify common mode signal. And if this tail source is not ideal, let's say we have a resistance here, right? So I'm doing the half circuit, we have a common mode gain. If this REE is infinite, then this will go to 0. And in Razavi, it explains nicely how we actually find the common mode gain. What is the, not just the formula, what is the understanding behind it. So we also need to find the common mode gain, the common mode signal when we apply differential. So basically, this is the common mode rejection ratio. So in the numerator, we apply a differential signal and we check the differential signal, and we look at the gain, okay? And in the denominator, we apply a common mode signal. So this common mode rejection ratio, do we want it to be 0 or do we want it to be infinite?